Governments use policies, legislation, regulations and taxation to influence people's behavior and address environmental challenges. Decision-makers aspire to evidence-based policy, and this creates imperatives to systematize knowledge transfer and application. Evidence-based decision-making has become a byword for good governance. In the UK, for example, over the last 3 decades the government has promoted evidence-based policy to replace ideologically driven policy, but its development has highlighted the challenges of dealing with environmental uncertainty and the need for transparency in the process. The effects of environmental uncertainty combined with issues of trust in government and science have impacted public perception and willingness to take environmental action. It is increasingly difficult for the public to understand or verify the evidence behind public policies, how it was generated, derived, or synthesized. These trends have further exacerbated public concerns about the role of science and amplified social inertia and apathy towards environmental policies. Considering that most sustainability policies depend on public acceptance and support through action, their effectiveness can potentially be diminished when public perception does not translate into pro-environmental behavior. Environmental policies often face a suspicious public, concerned on the one hand about the independence and integrity of science, and on the other about how scientific evidence is used to promote solutions to environmental problems or address policy needs. Environmental scientists have also raised concerns about often having little control on how their research findings are used, for example, as political ammunition, to support previously predetermined positions or to promote specific interests. Public discourse is increasingly distrustful of science, but is it a rejection of science or an erosion of trust in how it is applied? To understand the science-policy interface, it is important to understand the contrasting roles of science and technology in environmental challenges. While the relationship between the domains of science and technology has never been stronger, science and technology have different purposes, distinctive needs and divergent ways of viewing and knowing the world, and thus their relationship is often tense and complex. We question whether the convergence between environmental science and environmental technology, between the process of generating knowledge and that of applying it to deliver change, could be behind the growing public dissatisfaction and distrust of environmental science and policies, and propose a new perspective that distinguishes the roles of science, technology and society in surviving existential environmental challenges.
Science is about discovering, understanding, explaining and predicting patterns in natural phenomena, producing more accurate explanations of how the natural world works, regardless of potential applications. It is the result of deep curiosity and its goal is the pursuit of knowledge for its own sake. For the most part, science uses quantifiable inquiry that often involves testing researchable hypotheses, usually by means of a progressive research program, with data and experiments. In doing so, it may overturn networks of belief. Falsifiability is a virtue in a scientific theory, and science could be seen simply as an accepted process for establishing truth through repeatable observation and experimentation. This careful, rational, self-critical method of discovering knowledge provides a pathway to escape the contingencies of history. Humanity historically has applied scientific knowledge to solve problems, take decisions and reach today's level of development. Although today technology has come often to mean only the development and use of tools, techniques and machinery, here we refer to the broader process of the organization of knowledge applied to further the efforts of human practices, the application of knowledge, inventing and changing the world. Jacob Bigelow is often credited with coining the term technology in Elements of Technology in 1829, where technology was defined as the principles, processes, and nomenclatures of the more conspicuous arts, particularly those which involve applications of science. The strength of the relationship between science and technology was recognized by Lynn White in 1967, who traced their convergence back to the mid-1800s. In the historical roots of our ecologic crisis, natural science is conceived as the effort to understand the nature of things, and the marriage between science and technology, a union of the theoretical and the empirical approaches to our natural environment. According to the author, that scientific knowledge means technological power over nature can scarcely be dated before about 1850, marking one of the greatest events in human history. But it was the emergence of the term applied science, and the conception of technology as functionally dependent and culturally inferior to science, that marked the birth of their convergence, accelerated by the technological enthusiasm of the last century. The second phase of industrial development finds technology as the capitalist appropriation of scientific knowledge, leading to the confusion of technology with science today. For example, when out of the 1960s, there emerged intense anxiety about the effects of altered environmental conditions upon health, it was science that was blamed. U.S. President Johnson, handing out the 1968 National Medals of Science, reminded the attendees that, an aggrieved public does not draw the fine line between good science and bad technology. While technology is generally seen as the fruit of democracy and free enterprise, the implementation of increasingly complex technological systems involved organizational structures that became increasingly centralized and undemocratic. The development of technology, and thus the social development it implies, is as much determined by the breadth of vision that informs it, and the particular notions of social order to which it is bound, as by the mechanical relations between things and the physical laws of nature, as explained by Noble in 1977 in America by Design. The Battle of the Big Systems of the 1960s and 70s, involving historicists including Kuhn, Lakatos, Feyerabend, and Lawton, that investigated science's truth, rationality and objectivity, further accelerated this rapidly developing, sociology-inspired science and technology convergence. For example, Lawton in 1980 argued that the goal of science is to maximize the rate of progress in pragmatic problem solving. Further contributing to the science-technology convergence, has been the pressure for scientific research to deliver impact. This has been driven by developments such as the replacement of the Haldane principle that described the notion that decisions about what to spend research funds on should be made by researchers rather than politicians, in the UK in 1972, by the customer-contractor principle, according to which funds for scientific research should be directed by government. Similarly, in the U.S. it was the creation of the Office of Productivity, Technology and Innovation in 1982, that introduced a market-orientated approach and principles that still underpin important conventions between government departments and the science community. In line with the National Science Foundation in the U.S. increasingly considering the broader impact of scientists and their ability to articulate benefits to society in funding applications, the 2014 UK Research Excellence Framework introduced impact to assessing the quality of research and its benefits beyond academia to determine funding for research. These resulted in the boundaries between science and technology becoming blurred, with the need for change, rather than the search for truth, increasingly driving scientific research. Much of modern technology is based on science, but this recent association obscures crucial difference, and the failure to distinguish between science and technology has played a major role in obscuring the nature of science. With science directed toward practical goals, as opposed to pure knowledge and increasingly being sponsored directly by industry, technology has been seen as the solution that arises from epistemically driven research into practical problems, the so-called cascade model. The resulting worldview of technology as applied science sees the theoretical principles formulated first as science, and technical devices constructed by applying these principles as technology. In 1977, economist Richard Nelson challenged this model by asking why societies so rich and capable technologically are able to land a person on the moon but unable to deal effectively with many of problems such as slums and poverty, referring to the USA. In 2013, the question, how a country that cannot feed all of its people can find the money for a Mars mission, in The Economist, referring to India, indicated little to have changed. While few real-world problems can be solved by the application of science alone, for the most part, developed countries continue to train people as science specialists. Worse still, the educational systems of developing countries have been encouraged to follow the same pattern. As a result, today technology has become social production and the professional scientist an expert not only in their field but in its application for social change. Scientists in Western societies have enjoyed respect and embody an unassailable wisdom, previously the domain of religious leaders. Many factors have contributed to this, including the adoption of expert testimony in courts, and the introduction of government chief and departmental chief scientific advisors. Scientists assume the role of impartial observer, assumed to be relatively free from bias and guided by the scientific method's impartiality. Disciplinary experts are often called on to provide advice across a range of economic challenges, environmental problems and biological risks. In the UK, a landmark Parliamentary Select Committee report in 2000 recognised citizens' distrust of conventionally institutionalised science, following a number of high-profile technological controversies and crises which brought into question the accountability and autonomy of science and the role of society therein. There is now a widespread public perception that experts can and do disagree, that they are not infallible by virtue of their specialist access to some rigorous scientific methodology that can guarantee their objectivity, and that their purportedly disinterested advice may be influenced by professional, economic, or political considerations, or by their personal values. Social scientists have also voiced the concerns over the use of evidence by scientists, policymakers, and interest groups to justify decisions or to promote self-interest. They question the neutrality of scientific expertise. Several environmental controversies have been triggered by disagreements between experts, often resulting in prolonged, clamorous and unresolved public debate. Evidence provided by science can be mixed, incomplete, changeable or conditional on context. Yet scientific experts are expected to provide a consensus view and to recommend actions, often before the picture is complete. Tensions around the public role of science arise partly from the belief that the cultural credibility of expertise rests on communicating in terms of consensus. But while in science new knowledge is expected to challenge current consensus, the public sees scientific credibility strained. Loss of public trust often results from simplifying complexity or glossing over uncertainty or valid disagreements. Instead, scientists find ways to communicate why evidence may be inconclusive and why experts might disagree or make different judgments on the same data. Policy making requires public participation and engagement, and to some extent, this can alleviate problems of poor communication or lack of public engagement in science. For this, the public needs to be able to understand, be informed and be given access to all the evidence. Communication of science is about policy, ethics, politics, identity and power. Messages of apocalyptic peril and emotional appeals might be effective in addressing public apathy and inspiring change, but could also engender distrust or disenchantment, and deliver short-lived results. Efforts to isolate the technical or scientific issues often falter because of their narrowness and the ways in which the resulting communication is disconnected from human experience. Science's potential to empower lies in participatory practices that encourage shared knowledge, collaboration and shared ownership. The relationship between science and the public does not need to be one of blind trust. Scientists are not and should not be seen as modern priests, experts who pronounce on all manner of things with scientific knowledge as the ultimate authority. Contrary to popular depictions of science, science does not rely on authority as an indicator of truth. Results should always be subject to challenge from experiment. Science is liberating if it produces knowledge that empowers people to challenge dogma and beliefs. Knowledge itself is power, said Francis Bacon in 1597, and in the same vein, in 2003 Nelson Mandela stated that, education is the most powerful weapon we can use to change the world.